Testing 1, 2. Welcome to the class, Kutsum. Morning, can you hear me?
Yes, morning.
Morning, Kutsum. Okay, let's look at what we... do you have examples lined up for me or not?
No.
Okay.
Today.
What did you do this week?
This week I was occupied by a lot of tests.
Okay, so you haven't done anything new?
So, no, not really.
Okay, so we should be working on chemical rate or rate of chemical reactions and any questions you have on Newton.
No, that I'm just starting with at the moment.
You haven't started with that just yet. Is that correct?
No, I have, but then I haven't went far with it.
Okay.
I haven't went far with it, but I have started.
Okay, we'll look at some of the... I've got 2 examples that we can look at. All right.
Right.
Right, so basically this section is not that difficult, but can be problematic because there's a lot of reading and stuff that you need to understand. So we're just going to look at, so for instance, I've got a bowl or a flask there with some sort of acid in it. Let's call it hydrochloric acid. And I'm going to put some zinc in that, zinc pellets. So the pellets are going to go in there. And the hydrochloric acid is going to react with the zinc. So let's make our own equation there. Hydrochloric acid in solution with zinc solids. And that gives me zinc chloride in solution and hydrogen gas. And I'm just going to balance the equation like that. All right. Now, rate of chemical reactions basically has to do with the tempo or the rate at which that reaction takes place. Now, there's a couple of things that we can change to increase or decrease the rate. One of the things that we can do is to take our zinc pellets and just, well, grind it fine. So you just there's a difference between a big pellet that's grinded into smaller pellets. And that has to do with the surface area. The finer the pellets of zinc or the solid, the more surface areas there in which reaction molecules can react with it, and therefore the higher rate. You do understand that? Basically, if you take one block of zinc, you put it in there, it's going to react, and the same amount of hydrogen gas is going to come off from the reaction, but it's going to be slower than compared to when you refine the metal, or not refine, make it fine or very small pellets and put it in, because then there's a lot of total surface area in which the zinc can react with the hydrogen chloride. So if I make the pellets like finer, the tempo of the reaction or the rate of the reaction will increase. Also, I can play around with the hydrochloric acid's concentration. If I increase the concentration of the hydrochloric acid, then the rate of the reaction will also increase. Because then there will be more hydrochloric molecules per milliliter or cubic decimeter that can react with the zinc. Third thing I can do is increase the temperature. What happens if I increase the temperature of the solution or the reaction? That leads to increase of kinetic energy. So kinetic energy basically means if this is my zinc pellets in solution, and I increase the temperature, then these hydrochloric acid molecules will what? Move faster, or will have an increase in their kinetic energy. So they will be moving around in that flask at a higher tempo, and that means more reactions will take place in a shorter time. Is what I said kind of logic? Do you find it logic?
Mm.
Good, sir?
Yeah.
Okay. So basically,
Yeah.
the chapter
Yeah.
all revolves around
Oh,
this. And then there's going to be collision theory. Okay, that's a part you have to, that's going to be, I think it's Maxwell Boltzmann's collision theory. Anyway, it's just called collision theory. You don't have to know the name. That will explain, collision theory is the way that we explain these three changes we can make. So this is a bit of theory that you will have to go and learn before you start the chapter. So in your textbook, just try and find collision theory, and they will be representing it with graphs as well. Okay, so let's look at two examples, and then we chat from there. Right, this is a huge example. We might have to copy and paste more of these pages. Okay, I've got chromium metal. There we go. You might want to write down this equation. Chromium metal, and I'm going to add some hydrochloric acid. And that's going to leave me chromium chloride and hydrogen gas. And now I've got a little graph there on the right-hand side. And that graph just tells me the volume of hydrogen gas that comes off the reaction. The gas you can collect. You can have a little pipe, so you have a flask here. You seal it on top, and there's a little pipe like a straw that comes out. And that captures the hydrogen chloride, the hydrogen gas that comes off. And by capturing that, you can measure the volume of the hydrogen gas that comes off the reaction. And this is represented by this graph here. Okay, now look at this graph. It's got a gradient. So right at the beginning, the gradient is quite steep. What do you think does that mean? A steep gradient right at the beginning. The gradient there gives us an indication of the rate of the reaction. If I have a steep gradient, it means that the reaction rate is very high. So there's a lot of hydrogen gas coming off in a very short time. So as the reaction progresses, the gradient sort of becomes less steep. So here at around about 18 seconds, if we can make that 18 seconds, the gradient is not as steep anymore. It's becoming flatter. And then at 40 seconds, there aren't any gradient left. So there's no gradient. What does that mean after 40 seconds, do you think? You can also see that the volume of hydrogen gas after 40 seconds is not increasing. It stays at 3 cubic decimeters. So after 40 seconds, what do you think happened? What do you think happens?
the gradient, the reaction stopped.
The reaction stopped. So,
I'll say the reaction.
yeah, the reaction stopped. Basically, no more hydrogen gas is coming off the reaction, is being captured. That either means that my chromium is depleted, so there's no more chromium left, or it can mean that the hydrogen chloride's done. It's like all the moles of hydrogen chloride is finished. So let's just read. Chromium metal reacts with hydrogen chloric acid to produce a green solution of chromium dichloride and hydrogen gas, as shown in the balanced equation. Okay, then there's a girl, her name is Dana. She performs a series of experiments to test the effect of certain factors in the average rate of reaction between chromium metal and hydrochloric acid. In each of the experiments, so she does 3 experiments. Boom, boom, boom. I'm just reading to try and find out which one is in axis. Dana ensures that chromium is the limiting reagent. What does that mean? Chromium is the one that's going to be finished first. Limiting reagent or reagent means the one that stops the reaction. So we know that there's okay, limiting reagent. So we know that basically the amount of chromium you put in is used off first. There's an excess of hydrochloric acid. Okay. Dana ensures that chromium is a limiting reagent and is always completely covered by the same volume of hydrochloric acid in each of the same concentration. So she's using the same hydrochloric acid with the same concentration. She's just going to play around with the chromium. Okay, the reaction conditions for each of the experiments are tabulated below. So that she's made a table of each of her findings. Okay, she takes a single lump of chromium. It's like one little block of chromium, and the mass is 6 grams, and the temperature of the reaction is 25 degrees, and that is experiment 1. And now in the next experiment, she takes a single lump again, also 6 grams, but the temperature is lower. And in the final reaction, she takes fine powder chromium, and she only takes 4.5 grams, and the temperature is 25 degrees. Now, Dana observes that all 3 experiments, all of the chromium fully reacts in less than 80 seconds. Great. Dana collects the hydrogen gas produced at standard temperature and pressure and set time intervals. The results are of experiment 1. So that graph is experiment 1, the blue one. Now, they're going to give you that graph again on a answer sheet, and they want you to draw experiment 2 and 3. So maybe you want to give that a go. Try and draw experiment. Just quickly dot down that graph on your on a paper, and just try and draw 2 other graphs, the green one and the yellow one. See what it looks like. If you don't understand, it's fine. I just want to test basically what you have done in this chapter thus far.
Mm.
I don't have a memo for this. Should have made a memo for this. Oh, I don't have a memo for this. Okay. Do you want me to do it with you?
I'm almost done.
Okay, cool. It's going to be very difficult for me to draw exact precise on this page, but I'll try. I'm going to make experiment 2 red and experiment 3 blue. They didn't give us a lot of space with that graph. Good. Can we do it?
Yeah.
Okay. So experiment 2 is the same one block, 6 grams chromium, but the temperature is lower. Therefore, the rate will be lower. So the gradient will be lower. But it's 6 grams, so it will yield the same volume of hydrogen gas, but it will take longer so I just want to fix that. It will take longer for you to reach your 3 cubic decimeters of gas. So it will take longer to reach that, but you will also end up with the same amount. So that's your second experiment. Do you understand that? So the gradient will be lower because the
Yeah, I
temperature
understand
is
that.
lower. Therefore, I will have less collisions. The kinetic energy of the molecules will be less. So I'll have less collisions. So I'll have a slower rate of the reaction. But 3 cubic decimeters of hydrogen gas will form. It will just take longer. So I can't show that the graph as its maximum volume at 40 seconds, it must take longer. How much longer doesn't matter. It doesn't have to be 60. I'm not sure how long it will take. Then the next one, I've got less mass. So the mass of the chromium is less. Therefore, the yield at the end will be lower. I won't get 3 cubic decimeters, I'll get less, but the temperature is 25, same as the first one. And now I've got fine powder, which means the reaction rate will be higher. So I'll start with a higher rate. That's why I said I didn't give us a lot of space here. I'll start with a higher rate, but I will get less. I will get less hydrogen gas because I don't have enough moles of chromium because my mass is lower. So they'll mark you, give you a mark for a higher gradient. They'll give you a mark that it's lower yield, and they'll give you a mark for the curve. It's just by coincidence that the two is crossing there. We didn't make any calculations, so I can't say exactly where the lines will actually intersect. Is that cool? Do you understand this, good sir?
Yeah.
Great. Okay. Um, Other than using we are 2.3, other than using the volume of collected hydrogen gas produced over time, briefly describe one alternative method that could have been used to measure the rate of the reaction. In other words, if we don't collect the hydrogen gas, what else can we do to actually? And they say, in your answer, specify what equipment to be used and what measurements should be made. Okay, this is a difficult answer. Question. Not difficult, but I don't know, see how they can do it 3 marks. What we can do, we could have put this reaction on a scale. And then you put all the chromium in, and as the hydrogen gas escapes, the weight will decrease. So you could have taken the weight every half second. So we can use a scale and a timer. Okay, this is the equipment we need. Timer and scale. What answer specify what equipment should be used and what measures should be made. Well, okay, so we use a scale, and other equipment is a timer, and then the measurement we'll be making is the weight of the flask. As the hydrogen gas escapes, the weight will decrease. So we'll make a new graph with the same x-axis time, and now we'll just have weight on the y-axis, and our graph will slope down because the weight, with something like that, because the weight will decrease as the hydrogen gas escapes. Okay, now calculations. Consider the reaction conditions in experiment 1. I'm just going to go here, and we're going to copy 1, paste it there. And we're going to make this smaller. I think my screen is slightly smaller than yours.
I still can see clearly.
Good, because I'm struggling. Determine the total amount in moles of hydrogen gas collected at STP. Round your answer to 3 decimals. Okay, that's not too difficult. 2.4.1. let's just go back to that graph. You'll agree the total amount in volume is 3 cubic decimeters. So the volume we collected is 3 decimeters cubed. We can work out the mole. The mole is the volume divided by Vm. Now I can use Vm. It's 22,4. Why? Decimeters cubed. It's 22,4 because we're using this, we making this experiment takes place at standard temperature and pressure. And your VM value at STD is 22.4. Do you know that?
Yeah, I know that.
Okay, good. So the amount of moles is 3 over 22,4. And that you just pop into the calculator. Oh, I don't like that value. 0,1339. And they want 3 decimals. So the moles are 0,134. I can never remember if mole, one of them is American and the other one is British English. One is moles, other one is mole. Consider that the chromium metal is the limiting reagent. Calculate the percentage yield of hydrogen gas in the reaction. 5 marks. Okay, let's go back to that equation. Just want to copy that equation. Give me a second. Okay, they're not using delta H anywhere. I'm just going to take this previous calculation and make it smaller. Right, the question is, consider that the chromium is a limiting reagent. Okay, that's true. That was from the beginning. They told us that. Calculate the percentage yield of hydrogen gas. What is the percentage yield of hydrogen gas? And we have which reaction are they talking about? Because we're using 4.5 grams in the one reaction and 6 grams in the other one. Okay, all of these, sorry, I misread that. All of these are for experiment 1. And that's 5 marks. This is normal stoichiometry. So this is normal mole sums. Percentage yield is working forward, while percentage purity, we work backwards. So I want to give you 2 minutes. Think about that. See what you can do. Remember, we have in experiment 1, we have 6 grams of chromium. And you need to get a periodic table to get the molecular mass of chromium. I think it's 52. Do you have a periodic table there? Good, sir?
I don't.
You don't.
No.
Okay. The one I've got is not rounded off. Okay. Chromium is 52 grams per mole. Molar mass. So see what you can do. The nice things about these sums, if you don't know what to do, then you just work out the amount of mole, and then you get marks anyway. So can you work out the number of mole of chromium in the reaction? It's the mass divided by the molar mass. So the amount of moles is 6 grams divided by 52. And that is 0,11538 mole. Boom. You've got that?
Yeah, I've got it.
Okay, what now? Quick. I want to see if you can do some stoichiometry. Can you see that the ratio of chromium to hydrogen gas is 2 to 3 in my equation? 2 to 3. That means for every 2
Yes.
moles of chromium, I will be getting 3 moles of hydrogen gas. But I only have 0.11538 mole of chromium. So I'm going to make the hydrogen X just to make sure how much moles I'm supposed to get. And then I'm going to cross multiply. I don't know if you use this method. It's a very nice, easy method. You write down the ratio of
No, I
chromium to
use that.
hydrogen. You use it. Good. So let's
Yeah.
solve X. Let's solve X in that equation. So I'm timesing it with 3 and I'm dividing it with 2. And therefore X is 1,7307 mole. That is the amount of mole I should be getting of hydrogen gas. How much am I getting? I'm only getting 0,3134 or 1339, depending on which one you use. So I'm supposed to get 1,73. I'm only getting 0, no, that's wrong. That's wrong, Mike. I wrote this wrong. It isn't 1,7. It's 0,173 mole.
7. Yeah.
That's what I'm supposed to get in the, if I take this equation, I work it out theoretically, that's what I'm supposed to get, but I'm only getting 0,13. So the percentage is what? 0,134 divided by 0,173 times 100. That's the percentage purity.
So it's not an excess.
No, it's not. Something went wrong in the reaction. Okay. Consider that the chromium metal is limited. Calculate percentage yield. Percentage yield is only 77.46%. What basically happened here? The chromium isn't 100% pure, or the temperature we used wasn't optimal, or the pressure. Some of the hydrogen might have gotten lost in the process as we're capturing it. Do you understand? We're supposed to get 0,173 moles of hydrogen gas, but we're not getting that in the reaction. So our yield is not 100%. Do you understand? You can actually, by capturing the hydrogen gas in a balloon or something, you can actually, some of it can get lost. Some of it can diffuse through the walls of the balloon or whatever. There is some element of inaccuracy in this physical experiment. And we've just found it out. It's only 77.46% of the yield we should be getting. Do you understand this? Or do we need
No,
to...
I understand it fully.
Pardon? You don't
No,
understand?
I understand it fully.
Okay, good.
I have done this. I have done this section already.
Yeah, you've done this last year also. Percentage yield and percentage purity. Okay, good. Excellent. Calculate the average rate of the formation of hydrogen gas during the first 40 seconds. Okay, this can be problematic because we don't have an equation for this. 2.4.3. What is the average rate? Okay, average rate during the first 40 seconds. And interesting, they're telling you the answer is in cubic decimeters per second. So in other words, the rate will be the volume divided by the time in seconds. That's not difficult. What is the volume produced? 3 cubic decimeters. And the time? 40 seconds. So sometimes we get caught out with this because we don't have a proper equation for this. It's 0,075 cubic decimeters per second. That's easy. So it wasn't a difficult, this part of the chapter isn't that difficult. There's a lot of reading and a lot of graphs sometimes. Sometimes you have to draw your own graph. They give you, if they've given you a graph paper at the end, you must use that. Okay, another example. Now we have, there's a flask there, conical flask or aluminum flask is the same thing. The reaction of copper to carbonate with excess dilute hydrochloric acid, so that's an excess, is used in the equation. Okay, now this time they're using a scale. So when they put the acid and the copper carbonate in there, the weight of the scale is 170 grams. The weight on the scale is 170 grams. So the mass of that experiment, everything in it is 170 grams. State two ways in which the reaction above can be increased or the rate can be increased. Okay, you know that. We can increase temperature of the solution. We can grind the copper carbonate pellets to a fine powder. And what else? We can increase the concentration of the acid. Those are three things we can do. Good. Right. Now they give you a graph. Now, there's two experiments here. During the investigation, samples of pure and impure copper carbonate with equal mass are used. Now, they're telling you that the pure one is this yellow graph. And the impure one is this dotted line. Can make it blue. That's impure. Right. It's blue. Assume that all the gas formed during two reactions escape from the flask and that the impurities do not react. So two experiments are done. First, we do the yellow one with a pure copper carbonate, and then we table our findings and we draw a graph. So we start off with 170 grams, and then the rate of the reaction is quite high at the beginning, so there's a steep gradient, and then round about, 60, 50, 60 seconds. I can't really see. It looks like around about 60 seconds. The reaction stops. And for the impure one, the reaction stops when? Only after 70 seconds. I don't know. Let's just zoom in on that. It's also after 60 seconds. Maybe, yeah, it's very difficult to see on that small graph. Okay, anyway, it's probably not going to be a question. Can you hear me, Kutsu?
Yeah, I can. I say 50.
You said?
When I look at it.
It looks like 50 seconds, but the impure one...
I say 50.
Yeah, look, but the impure one isn't finished after 50 seconds. Only after 60 seconds. Anyway, it will probably not be a question because it's not clear. Right, write down the reaction time for the pure copper carbonate. Okay, the pure one. That's correct. I would also say 50 seconds for the pure one. Very good. I wonder if I have a memo for this one. Let's see what they think. They say anything between 42 and 50 seconds. Okay, whatever. 42. 42, I think it's wrong. Do you agree? I would say...
Yeah, no, I agree.
Yeah, it's not 42. I would say 48 to 50 seconds. Quickest. Okay, so assume that all the gas formed during two reactions escape from the flask and then impurities do not react. Now, calculate the average rate of the reaction of the pure sample over 20 seconds. So they're going to focus on the pure sample and they want you to calculate the average rate of the reaction. 3 marks. 5.3.1. First thing we need to do, we probably need to find out how many grams is of gas forms in the first 20 seconds. Okay, so we started off with 170 gram, and after 20 seconds, now I'm going to have to make this graph bigger. So that's 69.75, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So each one of those lines is 1. 2 of those lines is 1. So that line there is 76 at the end. Do you agree? 76, 77, 78, 79, 80. Yeah. See if you can read that place there exactly. I would say it's 169.76. You agree?
Yeah.
So 169.76. So that means there's only like a what? 0.24 grams used. Okay, is that correct?
Yes.
Or gas came off. So the weight of the flask decreased by 0.24 grams. So the rate will be in grams per second. It's the y-axis. Remember, it's the gradient is the rate. So it will be the change in y over change in x. So the rate would be a negative. So it will be the second y value, which is 169.76 minus 170 over 20 seconds. So that's a negative. Okay. And they just did this. I think they cheated. I wouldn't do that. I would just say, look, it's 170 minus 169.76 over 20. And that will give me what? Let's work that out. 0.012. 0.012 grams per second. That's the average rate of change. So it's basically a gradient between those two coordinates. You happy?
Yes.
Right, 4 marks. Percentage purity of the sample. 5 point, this is difficult. This is a difficult example. What is the percentage purity of the sample? Okay, let's look at the equation. Do we have an equation for percentage purity? It's the impure mass divided by the pure one times 100. This is percentage purity. Okay, I'm just going to move this way and take this graph, because we're going to use that again, out of the equation, out of the area. So now what can be quite difficult is the fact that you're not allowed to use that 20 seconds now. You have to use the whole reaction. And this is the problem, because I don't see my impure graph fully. It probably doesn't matter. We can use the 70 seconds if we want to. Yeah, we can use those coordinates if we want to. So let's start. Let's get the mass of the impure sample. So I'm going to do it after 70 seconds. Why? I can do it after 60 seconds as well, but the weight difference is not going to change. We have the same weight after 70 or after 60 seconds. So I'm just going to do it after 70 seconds, because then I'm 100% sure that both has fully reacted. So after 70 seconds, what is the weight of the impure one? What is the change, basically, of the impure one? The impure one started at 170 grams. And after 70 seconds, what's the weight now? Can you read off that? Damn.
I will
Big
try
problem.
to.
So each 2 lines is 1 unit. 1, 2, 3, 4, 5. So I'll say it's round about here. Do you agree? It's 1, 2, 3. So that's 169,78. One six nine comma
Yeah, I agree.
8. I would say that's pretty accurate. In the exam, they'll give you a big graph, bigger than ours. So this is a 0,22 gram of the carbon dioxide that came off. Or the flask got lighter by 0,22 grams. And then what about the pure one? It also starts at 170. Okay, what would that weight be? It's this line here. There. So that is 1, 2, 3. So it's 169,73. 169,73. That is just what? 5 more. So 0,27 grams. So the percentage purity is the impure mass change, 0,22, over the pure one, 0,27, and I times that with 100. It's a lot of logic in this, but it's kind of confusing because you have to work with graphs. 81,48% pure. So I'm just going to put that there so you can write it down.
Already gone.
Excellent. Okay, done. Maximum, okay, calculate the maximum volume of carbon dioxide produced during the reaction of a pure sample of carbon carbonate if the reaction takes place at standard conditions. Right, okay. Where can we do this? So what is the maximum CO2 gas at STD conditions? Okay, what do we know? That the mass equal 0,27 grams. Is that correct? This is probably a maximum volume. I don't see how they can refer to maximum what? Maximum what? The maximum mass we have, it's 0,27. So let's just look at that question again. Yeah, it's a maximum volume. And this we can all do. The moles is the volume over Vm. And STD means that the Vm value is going to be 22,4. So the volume equals the moles times Vm. I need to just get the mole value there. The mole will be mass over molar mass. And that will be 0.27. The molar mass of carbon dioxide is a 12 plus 16 times 2. Let's get that. I'm going to write 6,13636 times 10 to the power of minus 3. I'm going to write that down, but I'm going to use the answer button in my calculator to do the calculation. So the volume is 6,136 times 22,4. So it doesn't matter really what I write there, as long as I keep that answer in my calculator and at times it was 22,4. And then I get a volume of 0.137 decimeter cubed. Now, they probably want 2 decimals, which is quite irritating because it's a huge difference actually. 0.14 cubic decimeters. Okay, sketch a graph of the volume of gas produced versus time of the reaction of the pure one. Indicate we don't have we can sketch a graph, but we can't do an accurate one. Okay, so let's just skip that. We don't have graph paper. But they're not asking. Indicate the reaction time on the axis, x-axis. Okay, we can do one. Okay, so let's just do that. I'm just going to take this out so we can use the space underneath that. Okay, let's just do a graph without graph paper. So there's my time in seconds, and this is volume in cubic decimeters, the y-axis. Okay, what's going to happen? Right at the beginning, there is no volume. And then the volume quickly increases as the reaction starts. So it will have steep gradient. And then somewhere it will flatten down. So remember we said 50 seconds. After 50 seconds, the pure sample is fully done. So I'm going to do a 50 seconds there. And you'll probably get 1 mark because you have the 50 seconds there, and 1 mark because you've got a curve there, indicating that the gradient is steep at the beginning, it shallows down, and then at 50 seconds, there's no gradient. Why? Because there's no more gas forming. Okay. Right. So that gives you the indication of the type of questions you're going to get in this chapter. And I think you're doing all right. I want to test.
No, I also think I'm doing good.
I'm going to test you on something quickly. Last year's work, Newton. There's an angle of, say, 30 degrees. I have a block there. It's 10 kg. There's a coefficient of static friction of 0.2. Right. I want to know, okay, the block is in rest. And that's indicated by that S there. Static friction means that it's not moving. I want you to work out what is the friction, the force on the block. You can either just quickly write that down, ask for a minute or two to think about it, or you can just lead me into doing it. Or you can just tell me, look, I haven't looked at Newton for a long time. I don't know what's happening.
I'll try to do it.
Okay, good. You can ask questions. The first thing you always have to do with Newton is draw a free body diagram, eh? Otherwise, you're going to struggle. I think there's two ways of doing it. Okay, which direction are you taking?
Which direction?
Did you draw a free body?
No, to everybody diagram.
Okay, let me just get more space for myself here. Okay, so you've got FG parallel there and FG perpendicular there. Is that correct?
Yes.
Good. Okay, what should I do then? F net equals 0 because the block isn't moving. So now I'm choosing the downward for movement as positive. So the FG parallel force is positive plus a negative friction will give me 0. FG parallel is mg sin alpha, and that equals friction. Mass 9,8 and then sin 30. That's the friction. And that is 49, I think. So the frictional force is 49 newtons up slope.
Okay.
That's one way of doing it. You could have also said if static, the frictional force static is mu Sn. Remember that equation? And then you can work out the normal force.
That's the one I used.
Okay, the normal force plus a negative Fg perpendicular force is 0 because the sum of those two forces are 0. Just going to move this down because we'll need, okay, no, we don't. The normal force is Fmg cos alpha So the frictional force is the 0,2 times mg cos alpha. And that is 0,2 times the mass times 9,8 cos 30. And then I type that in the calculator. There's a problem. Normal force mg. Is that right? Cos alpha. It's correct. Why do I get 16? Did you get 16,97?
16,97.
That's wrong.
Yeah.
No, its calculation is correct, but it should be the same. Oh, I understand why it's wrong. I should have tested the 0,2. I didn't test. I only thought of this method. I should test the 0,2. The 0,2 isn't high enough. That 0,2 is wrong. What I'm trying to say is if you lift up the slope 30 degrees and you only have that 0,2 as a static coefficient, the 10 kg block will slide down. Okay. So that 0,2 should be a higher value. Can you see the first calculation doesn't use the coefficient of static connect, the coefficient. It doesn't use it. It ignores it. That value should be much higher. It should be something like 0,65 or something.
Okay.
Sorry, I didn't test that. 0,65. So let's try 0,65. I hope it works. No, I can't guess the value. Sorry, I didn't work out this example. Let's do just tan 30 on your calculator quickly. Yeah, it's not going to work. It must be 0.577. Okay, sorry about that. I should have tested that value there before I actually put it in. The 30 degrees is way too high for such a low coefficient of static friction. I'm just going to multiply it with 10. Just give me a second so I can quickly fix this. Yeah. Okay, so it's going to be tan 30, which is 0,577. 0,577. Okay, so 0,577. If I put that in, I get 49 newtons up slope. I'll explain to you now. So tan alpha is me S. So that static coefficient there equals tan 30 if the object is in rest. So I should have just tested it before I started with this. Sometimes this is a nice way of doing it, but this is easier if you've got the coefficient. Do you understand? I could not have guessed the coefficient is 0,2 and guessed the angle. The angle and the coefficient works together. Okay, I think that's it. I'm happy you can do this. Remember, in the June exam, you must be able to give account of your grade 11 work as well. So we'll just, every week, just throw in a bit of something just to get us into that groove again. Okay, Kutsu. Have a nice weekend.
Thank you.
Okay, keep well. Remember to accumulate questions as you're working.
Bye.
All right. Cheers, eh? Bye-bye.
Yeah, well, I'll have a lot of questions. All right, bye bye.
Bye-bye.